Welcome to the fifth video on equations and inequalities for Year 12 A-level/AS. So today we're going to be looking through inequalities in particular and also graphing inequalities to help to solve them. We're going to also be looking through today the problem of multiplying or dividing through by a variable when you've got inequalities in terms of switching over the inequality symbol. So we need to take more care when dealing with this. So it's all to come up in this session. But before we get started on that, you've guessed it, here's 4 warm-up questions for you to try. Try these first, and then only after you've tried them, use the video to self-assess and see how you've got on. So let's have a look together at question 1 first of all. So question 1, we're looking at a projectile being thrown, and its height, h, can be modelled as a function of time after launch by the below equation. H is measured in meters, and t is measured in seconds. So it's saying here to find the time after launch when the projectile reaches its maximum height, and to also state this maximum height. So looking at this and not thinking about it too much might seem intimidating, but what we need to do is remember that this is a quadratic in completed square form. And once we know this, we need to remember what the constant inside the brackets tells us and the constant at the end. In particular, what does 1.2 and 6.2 tell us? Well, we need to remember that these two numbers here essentially tell us the coordinates of the turning point of the quadratic. In other words, we know that this height is going to be a maximum when t is 1.2 seconds. So we can just write this in now. So maximum height is after 1.2 seconds. Because this number here is 1.2. That's as simple as it is. Whoops, one colour. I needed that in yellow. There we go. And this number here tells us the y-coordinate of the maximum. In other words, the maximum height itself. So the maximum height is going to be 6.2 meters. So after 1.2 seconds, it reaches its maximum height, which is 6.2 meters. And that's all there is to it. There's no real solving going on. It's just a case of identifying that you know what the completed square version of a quadratic tells us, which is really important. Question 2, find the value of each of the following. So rules of indices and surds, essentially. So what we need to remember for this one, for 5 over 3 to the power minus 2, is that if we have something to the minus 2, or any minus power, it's the same as the positive power, but the reciprocal of itself. So this is the same as turning this on its head to the positive 2. Okay, now we can square the top and square the bottom separately. So 3 squared becomes 9, and 5 squared is just 25. That's all there is to it. There would have been other ways to have done it. We could have done 25 over 9, then to the power minus 2, which would have been 1 over 25 over 9, then flip the fraction, would have got us this as well. Over here, 81 to the power 3/4. Well, what I'd suggest to do is always do the root first, then the power after. And so do the 4th root of 81, and then cube. So, fortunately for us, the 4th root of 81 is an integer. So what number multiplied by itself 4 times gives us 81? Well, that number's 3. So the 4th root of 81 is 3. We then cube that, so 3 cubed, that gives us 27. Question 3 of a warm-up, simplify 10 root 6 all cubed over root 24. So there's a neat little trick to this one. Root 6, by the way, just means root 6, root 6, root 6. And root 24 actually has root 6 as a factor of it, so we can split 24 into 6 times 4. So we can rewrite root 24 as root 6, root 4. So just to highlight what I've done here, so I've just rewrote root 6 cubed like this along the top. On the bottom, I've just split root 24 into its root factors. Now what we can see is we can cancel a root 6 on the top and on the bottom. So 1 root 6 will cancel there and here. So on the top we're going to have 10 times root 6 times root 6. Well, root 6 times root 6 is just 6. And on the bottom, the square root of 4 is obviously just 2. So 10 times 6 is 60. Divide through by 2. That one just becomes simply 30. Last but not least, question 4. Solve the inequality 4x minus 5 over 7 greater than 2x plus 1. This should be very simple, but just serves as a refresher from GCSE really, if nothing else. So multiply through by 7. That gives us that 4x minus 5 is greater than 14x plus 7. If we subtract 4x from both sides, we get minus 5 is greater than 10x plus 7. And subtracting 7 from both sides, we get minus 12 is greater than 10x. And if we divide through by 10, we see that x must be less than minus 1.2. So x is less than minus 1.2, or if you wanted, you could leave this as a top-heavy fraction and say minus 6 over 5. You could call it minus 1.2 if you'd prefer. Either way is absolutely fine. So what I'm going to do now is just get straight in to solving quadratic inequalities via some worked examples. We're not going to go into any notes, just let's get straight into it. So first of all, let's find the set of values for which 3 minus 5x minus 2x squared is less than 0. Provide a sketch of a function to illustrate the solutions. So because we need a sketch, what I'm going to do first of all is just get these coordinate axes ready. There's also one of two ways of doing this. What we could do is we could divide through all of this by minus 1, but that means we'd have to flip this inequality sign. Another way we could do it is to factorize out the minus 1, not flip the inequality sign, and then factorize the other bit of this quadratic without having to change the inequality symbol. And that's what I'm going to do. And so I'm going to just take this here and factorize out a minus 1 for the whole thing. So minus 2x squared becomes positive 2x squared. Minus 5x becomes positive 5x. And positive 3 becomes negative 3. So this bit inside the brackets will factorize out. We can use the AC method. So if we do 2 multiplied by minus 3, that gives us minus 6. So can we think of two numbers which multiply together to give minus 6, and when we add them, it gives us 5? Well, those numbers are going to be 6 and minus 1. So we can partition this 5x into positive 6x and minus 1x. So this bit here, the 2x squared plus 6x, we can factorize that into 2x brackets x plus 3. And minus x minus 3 has a common factor of minus 1. So that becomes minus 1 brackets x plus 3. All of that less than 0. So then we can put the 2x minus 1 inside its own bracket. And we're effectively done. In fact, what we could do, we could just write minus without including the minus 1. But it's exactly the same thing. I'm not really changing anything by doing that. But now we can actually see where the critical values will be, where this is equal to 0. We can just do this by inspecting the brackets. So the critical values are going to be where x is equal to a half from this first bracket, and from the second bracket, this is going to be equal to 0 when x is equal to minus 3. Okay, so we know where it's going to cross the x-axis. It's going to be crossing at a half and minus 3. As well as that, This is going to be a negative quadratic, so it's going to be a N shape. So the next thing we need to do is just to sketch this on our graph. So once again, in advance, forgive me for my rubbishness at sketching graphs, but here goes nothing. Something like that. So it's going to cross at -3 and +1/2. So I can label these in. So we're after where this function is less than 0. Now this is where the sketch comes into its own. This is essentially where this curve lies below the x-axis, where the y is a negative value. So we can see here there's going to be two strands to this. One is where x is going to be less than -3. The other bit is where x is going to be greater than 1/2. Okay, so what we can do is we can take our work and what we've done here, okay, and then think about what our solutions to this are. So looking at the graph along with this, we can see that to solve this, either x must be less than -3, or we could have that x is greater than 1/2. This question doesn't ask us to put it in set notation, but I'm just going to remind you of how you could do this using set notation. So in set notation, we have two non-overlapping regions which are both valid. So we could say that we could have x such that x is less than -3, or, so the union symbol, we could have x such that x is greater than 1/2. So this standard form is absolutely fine. I'm not asking you to do set notation here, but just to show you what set notation would have looked like, that's what it would have been in set notation. Another worked example. So worked example 2. So we need to find the set of values for which 12 plus 4x is greater than x squared, and then hence find the set of values for which 12 plus 4x greater than x squared and 5x minus 3 is greater than 2. So illustrate these solutions on a number line and give your solutions in both standard form and set notation. So what I'm going to do first of all is just give myself a space to work on both of these inequalities, which I've done over here. And as well, I'm going to put a number line down too, just for the sake of helping us. So first of all, let's have a look at 12 plus 4x being greater than x squared. So I'm just going to highlight this one in yellow. First of all, what this can be done is it can be rearranged to be 0 is greater than x squared minus 4x minus 12 if you just subtract the 12 plus 4x on both sides. This will now factorise quite nicely, and so two numbers that multiply to minus 12 yet add up to minus 4. That's going to be x plus 2 and x minus 6. So if you imagine a sketch graph of this, the critical values here are going to be where x is minus 2 and x is positive 6. So just get this straight. Okay, so for critical values, I'm just going to sketch in. So we have a y-axis and an x-axis. It's a positive shaped quadratic, so it's going to be U-shaped. It's going to have roots at minus 2 and positive 6. So it's going to be something like this. And come back up again. So that needs to be less than 0. And so these roots are going to be in between minus 2 and 6, where this sketch is below the x-axis. So we're looking at this region here. So just label on this as minus 2, and that's positive 6. So therefore we see x must be between minus 2 and 6. So if I were to label this on the number line, it'd be between -2 over here and 6 at this end. Hollow circles because it's strictly less than, then we have a straight line connecting the two together, like so. Let's make that a bit longer so it actually connects. There, that should do. Well, close enough. So the solution to this one I've put here, -2x minus 6. If I need to do the same for 5x minus 3 greater than 2. So what we need to do first of all, I'd suggest would be to add 3 to both sides. So if we add 3 to both sides, we get that 5x must be greater than 5. Divide 3 by 5 shows that x must be greater than 1. So this solution here ends up being just x greater than 1. So we put a circle on top of where it says 1 here, and then an arrow pointing in the greater than direction. So this solution is going to be like this. And so if we look here, this needs to be true and that one needs to be true. Okay, so whereabouts using this number line are both of these inequalities true? Well, it's going to be in between the overlap between these solutions. So we're looking here at between 1, yet not including 1, and 6. And so the actual solution range we're interested in is x being between, yet not including, 1 and 6. So we're interested in this range here. So the number line helps us to see where these overlap. Where they overlap, that's where one and the other are true. So therefore we can say that x must be between 1 and 6. So in standard form, we have this. And using set solution, so set notation, it's going to be like this. We're going to have the curly brackets and x such that x is between 1 and 6. And so that's just a way of writing them in the two different forms. Now, a little bit of caution, some warning here about when you're multiplying or dividing through inequalities by a variable. This will be familiar in some way from GCSE. So just to remind you, when you multiply or divide through an inequality by a negative value, we must take extra care to remember to switch the direction of the inequality symbol. So if the logical reasoning of this is in any doubt, just consider a trivial, easy, obvious inequality that is true. So for example, I've said here, 5 is greater than 2. Obviously that holds true. Yet if you were to multiply both of these sides by -1, without swapping this inequality sign, this would become -2 is less than -5. That's clearly false because -5 is less than -2. -5 is smaller. So to keep it true, therefore what we must do is flip over the inequality symbol so it faces the opposite direction. And we need to do this every single time we multiply through or divide through by a negative factor. The problem is though, when you multiply through not by a constant term but by a variable, usually it's x, then by its nature a variable may take both negative and positive values. So how are you to know if you're multiplying through by something positive, stuff you don't need to worry about, or if it's negative, something where you'd have to switch the inequality symbol? Do you switch it or do you not? You can get around this by not multiplying through by just x, just y or z, whatever, but multiply through by something you know strictly is non-negative. So you might choose to multiply through by x squared, because something squared is always non-negative. And so the following example just illustrates how we can use this technique to help us. So worked example 3 I've called it. Find the set of values for which 6 over x is greater than 2, where x is not allowed to be 0. So it might be tempting to multiply through both sides by x. But if we were to do that, would we have 6 greater than 2x? Or would we switch the inequality symbol the other way? It's confusing, yeah? So what we do is we use the idea I mentioned just previously. So what we can do here is actually multiply through both sides by x squared. Not by x, but by x squared. So what we get, 6 over x multiplied by x squared. One of the x's cancels, the other one goes on top. So we get 6x must be greater than 2x squared. This can now be rearranged. And first of all, actually, let's divide through by 2. So 3x is greater than x squared. Minus 3x on both sides, we get 3x on the other side. So 0 is greater than x squared minus 3x. We can now factorize this right-hand side to obtain that 0 is greater than x, brackets, x minus 3. We can now graph this easily enough, with a sketch at least. So this is going to have roots at 0 and positive 3. And more than that, it's going to be a positive quadratic because it's a positive x squared. And so a sketch of this one would look something like this. Going through at 0 and back up again, coming through at 3. So we're wanting this to actually be less than 0. And so this is going to be less than 0 where x is in between 0 and 3. That's where it's below the y-axis. And so the bit of this we're interested in is this range here. So therefore the solution here is that x is between 0 and 3. Question 4, let's use some set notation to describe the set of values of x for which x squared minus x minus 30 is greater than 0 and 2x plus 7 is less than 11. So first of all, let's start with x squared minus x minus 30 being greater than 0. So this will actually, whoops, wrong colour, keep doing that, never mind. This will factorise quite nicely. So two numbers that multiply together to give us minus 30 and add up to minus 1. We could pick for those numbers positive 5 and negative 6. So it's going to be a positive shaped quadratic with critical values at minus 5 and positive 6. So if we were to sketch this, x against y, we're going to have something that looks something a bit like this. So for the first bracket, like I said, that's going to have a critical value equal to 0 when x is equal to minus 5. Over here, x being 6 will give the other critical value. So the graph is going to look something a bit like this. Well, over here we have minus 5, up here we have 6. Now we want this to be greater than 0, so we want this to be higher than the x-axis. And so the range we're interested in here is where x is less than 5 or where x is greater than 6. So the solution is either that x is less than minus 5 or that x is greater than 6. Let's now consider 2x plus 7 being less than 11. So if we subtract 7 from both sides, we have 2x is less than 4. Then we can divide through by 2 to obtain x has to be less than 2. So we want to use set notation to describe when this holds true and simultaneously this holds true. So whereabouts do these sets of solutions overlap with this set? Okay, so we can just use what we've got here so far, but I'm going to show you how a number line has its uses too. And so we want x to be less than 2, you see. And so if we imagine a line where x is equal to 2, we need x being less than 2. So we're looking on our graph sketch for x being down here. Okay, so the only bits of this solution, which would also satisfy x being less than 2, is this region here. This region doesn't count because this is where x is greater than 2, and so the solution we're after is actually that x must be less than 5. Sorry, x must be less than -5, this bit here. Now, we can use a number line as well if we wanted. So using a number line idea, we'd have something that looks like this. Okay, so these are solutions in yellow for the yellow inequality, and for the green inequality here, 2x plus 7 being less than 11, x being less than 2 I've highlighted in green. And so where they overlap is down at this end here. So it's where x is -5 less than that. That's the only bit of the number line where the yellow is overlapping with the green, where x is less than -5. Up here, there's no overlap between yellow and green. So that's how a number line could have helped us. Take care though, it did ask us for set notation for this. So in set notation, we're going to have written, we need x such that x is less than -5. And then we're all complete. You've guessed it, now it's over to you. So on page 50 you'll find exercise 3E. I want you to try all questions on that just to give you a great grounding on how these inequalities and graphs go hand in hand. So a graph sketch is often crucial, and it also is useful when we're dealing with inequalities involving the discriminant too. So don't shy away from doing a sketch of a graph, not a plot but a sketch. So after all that practice you should be an expert on these. If ever you get stuck, as ever, please do ask me, either in class or on email, and keep working away hard. Okay, you'll hear from me again soon in the next video. Take care and be in touch. Thank you.